Okay, thank you very much for inviting me. It's very nice to be here. This became a huge conference, so I'm a little bit impressed by all the people that is here. Thank you very much. And yeah, this is essentially an exercise I'm going to tell you today, done in collaboration with a couple of co-authors. The basic idea is this consideration. So we start with this consideration. Okay, so predictive accuracy, that is the information which is reflected by prices in a market model, is linked with the selection mechanism taking agent J. He can exploit his knowledge essentially to outsmart and become richer than agent J. Ultimately is going to essentially get almost all the money in theory. And the interesting consideration, which is related with this selection mechanism, is the fourth point. Not only agent I becomes richer, but being richer is also going to affect prices more. So if this mechanism is in place, actually prices will reflect on the long run the best available learning model in the market. Okay, so in this way, a market works like a learning mechanism. Okay, if this takes place, and this is actually the point, if the learning of agents takes place in a well-defined situation in which the truth can actually be learned, then this is what happened. But the question is, okay, what happens if instead we consider a situation in which used by agents are misspecified, which means that the reality, the true model that drives the dynamic of the system, cannot be learned. Okay, they can build some approximation of it, but they cannot learn it. Okay, now there is so essentially we are going to investigate learning taking place in a population of agents, and we are going to study, okay, which learning models are more effective than others when the situation is a misspecified, okay, when the reality is misspecified. Now, there is one important point in this investigation that we should take into consideration. When we describe the agents in an economic model, information is actually only part of their behavior. Okay, they collect information, they learn about the reality, and then they decide what to do with this information. Now, it might be, and this is pretty easy to find example of this, that the two things together can actually correct each other. Okay, so I might have agents that actually learn badly, so they have bad learning algorithm, but they also make mistakes in using this information, and the mistakes they do, they actually correct the error that will be induced by a wrong learning mechanism. So if I really want to focus on one aspect of the dynamic, which is learning, I should find a way to essentially neutralize the problem of building portfolios, for instance, in a financial environment, building portfolios starting from this information. The way to do it is avoid portfolios, and this is essentially so having a framework in which the decision of agent is by definition always optimal, the best they can do, and in such a way the only issue and the only problem is how much they know about reality. So right now I'm going to spend a few slides, and this is basic part of the speech to describe how we did it. Okay, how you can actually build a model in which you are sure that the behavior of agents is the most rational and best for them as possible. Okay, the idea is using what is known as the Arrow-Debreu economy. The idea is, so we have a time structure. Don't worry, I mean, this is just a list of features, and then I'm going to explain them in a couple of slides. So there is uncertainty in this model, and in each period of time, there are S possible state of nature. So this means that each day there are S possible future tomorrow. The economy is populated by a different agent having different beliefs, and the beliefs is the probability they assign to the possible futures. And each agent, we will see, maximize a given objective function of their consumption. Okay, but let's see a little bit of detail of the stuff. So this is the structure of the economy. Okay, this direction is time. These are days or months or weeks, whatever time scale of the model. And at each day, as you can see, there are S possible states in which the economy is. Okay, and these are replicated for each day. I use the variable S1 to indicate the state of the economy in the first day, S2, the state of the economy in the second day. You can, above this sort of structure, you can build a trajectory, of course. Okay, so you can see what's the one history of this economy. One history starting at date 0, which is common from everybody, and then the history goes on and stops here, for instance. Okay, so this is an history of length t. So history until t is essentially this trajectory. Okay, ending here. I'm going to denote with sigma t all the histories of the economy, that is a sequence of state of nature until t, and I reserve the symbol sigma without any other specification for infinite, for a complete sequence with infinite length. There is another way in which we can describe the same situation, which is using a tree. Okay, this is a tree in which essentially the story are the node. Now each node is a partial history. So now each node of this tree is actually the sigma t of the previous slide, and now the evolution of this model is through the nodes of this tree. At each date, sigma t is the partial history. Remember this, you can see it also as a trajectory in the grid I showed you before. For each story, there is a partial story. So I can indicate it with sigma minus. This is partial story before, just the day before or the week before sigma t, and future story. So this is all the possible story in the following dates. Okay, what are the variables of this model in each node? So just focus on one moment in time. So given one history, I have 3 variables essentially that enter in this model. The first one is the endowment of the agent, so how much the agent get from outside of the economy. You can make assumption about it, not so relevant. This is the consumption of CI, is the consumption of agent I, and this is a vector. So you have an E and a C for each single agent, and you have the price, Q sigma T. Okay, this is the price of what? Of the consumption good at date T. Very good. So this is the problem. So the agent inside this situation, the agent is required to maximize this equation. Okay, so this is the utility function of the agent as a discounted utility function. This is the consumption. Okay, this is the consumption of agent. So how much the agent can eat in the history sigma t, and the agent is going to maximize this discounted utility with this constraint. This is called the budget constraint, and this constraint tells essentially that the value of what you consume at date 0, thank you very much, the value is the first, very good, the value of what you consume cannot be CI time Q, sum over all history cannot be higher than the value of what you are endowed with, so what you get from outside. So each agent is required to solve this equation. There are n agents, and then we have a market clearing condition, which is essentially a physical good market clearing condition. That means the aggregate consumption of the agent must be equal to the aggregate endowment. You cannot consume something that does not exist. If we take all these equations and maximization together, what we are going to get at the end, we are going to get a price at each date, and we are going to get a optimal consumption level, strictly positive at this date. Okay, so, and the point is, okay, all this discussion was to say this is maximally rational. Okay, so all agents, they take into consideration, they know that the future exists, the market is complete, they trade whatever they want, they are free to trade as they see fit, but the only thing that is truly important here is that they do it based on a belief. Okay, so all this structure is based on what the agent believes about the future, which is captured by a measure on the sigma process agent I. Okay, of the agent I. So this is an individual agent. Now let me move a little bit further. Okay, so what? So we say we have the prices using the price Q. Just to message, the price Q can be used, which is essentially a process, is essentially what is called a risk-neutral measure. This is essentially a risk-neutral measure. You can use it to price any possible financial contract you want. But let me notice something important here, and now I quantify what I said before about selection. Remember this equation, okay? This was a market clearing condition, we say. Okay, what happens if the consumption of a single agent actually becomes the aggregate consumption? This is the case we described before. So this is the agent that becomes enormously rich, okay? It can consume everything. Well, what happens is the relative prices essentially converge to, okay, let's ignore this part, this is not interesting, but relative prices converge to the conditional belief of the agent, okay? So this is the point. So if one agent consumes the majority of the allocation, then prices, the process of prices is essentially the process of the beliefs of the agent, okay? Which means that in order to understand if the market is able or not to select the best agent, we have to look at which agent is going to consume the most in the long run. Now, but in order to give meaning to this exercise, we need to introduce a new variable, which is the true process, okay? What we said before. Imagine that the agent is able to learn the truth. Okay, let's assume that the true process exists. Given these two processes, we are essentially looking for this kind of agent, so agent that asymptotically, in this, using this measure, they asymptotically, almost surely dominate the economy, so they eat everything, or at least that they remain alive, okay? So they can somehow contribute to the definition of the asymptotic prices, okay? This definition, they are not based on the individual belief of agents. That's the important. They are defined in terms of the true probability that enters into the model now. Until now, I didn't introduce true probabilities, okay? Agent, they can solve the problem without knowing the true probability. The only thing they know are the individual beliefs. Very good. Now there is a trick. This is the most technical slide of the paper. And now there is a trick in which we can essentially translate the dynamic of consumption of agent into essentially a relative likelihood ratio. Okay, that's the trick. And we are doing it by using recursively the first order condition of the optimization problem. Okay, so what you discover is that essentially this ratio, that is called the ratio of marginal utilities, is essentially equal to the ratio of the model of the agent. Okay, so now let me explain the meaning of this stuff. Imagine, so this is, you can think about this ratio as a likelihood ratio. Okay, you are sampling from a process and you build your likelihood under. So agent J use his own model to compute his likelihood. And agent J cannot compute this likelihood. We use the model of agent J to compute this likelihood, agent I to compute this likelihood. Now, what happens to the likelihood we know what happens to that. The likelihood they goes to zero, of course. That's a product of probability, okay? So they typically goes to zero. What's the likelihood that goes to zero more slowly? The likelihood of the best model, okay? The likelihood of the best model goes to zero more slowly than the likelihood of the worst model. So if I is a better model than J, this ratio is going to zero because Pj is going to zero faster than Pi because model I is better than model J. On this side, we have a beautiful zero. Well, what can we do on the right side? So on the right side, how can we obtain a zero? We cannot obtain a zero from the numerator. Why? Because this is strictly positive by assumption. The only way we can obtain a zero is that the numerator goes to plus infinity, which means that the consumption of agent J goes to zero. Okay, so we learned that if model J is worse than model I, the consumption of agent J goes to zero, okay, with respect to the true probability of the process. Okay, this is a little bit technical. Just to explain the slide, you can characterize and describe effectively. This is from the computational point of view very much. This is useful. You can describe this likelihood ratio using the relative entropy. So we introduce this definition. You are going to see it on the picture, but the idea is that they are equivalent. Okay, so you can essentially describe the log likelihood ratio of the model of agent I with respect to the truth using relative entropy. But the idea is the lower the relative entropy, the better the likelihood of the model used by the agent. Okay, very good. So until now, this is a theoretical framework. Now horse race. So now I'm going to consider different models and compare their performance. Okay, this is the exercise when in a framework of misspecified model. So the first class of learning process that I use are called under-reaction learning, and that essentially extend the idea of Bayesian learning. So the idea that the agent learns of a given set of models, updating the weight the agent assigned to the different model following this rule. If you put lambda I equal to 0, essentially this part disappears and you have Bayesian learning. So essentially the weight of the different model are updated proportionally to the probability that the different model assigned to the realized state. Okay, so this is Bayesian learning and this is generalization. So this is Bayesian and underreaction. But there are also other possibilities we can explore. We call this limited memory Bayesian, which is essentially an agent who forgets the past. So this is they ignore the past. Let's use the most extreme assumption. The agent just consider the last realization. Okay, so you forget all the past yesterday. Okay, this is the mosquito agent. Okay, no memory. No, sorry, the redfish agent. Okay, no memory of the past. But there are other alternatives. So another alternative that you are going to consider is moving average learning. Okay, so starting from a baseline model, now the agent essentially take a moving average of the observation of this baseline model. The question is taking average a good idea? Let's see. Okay, and let's actually see in a very simple example, the simplest essentially we were able to put together. So now the process is binary, which means there are two states of nature for each date. And the fruit is described by probability of getting 0, probability of getting 1, of course. Okay. Now agent are learning on two models. The two models are two IID models. Okay, like coin flipping. This is the side the probability of head and tail, and the agent they learn on two possible models that define the probability of head and tail. But look at here. In general, both pi1 and pi2 are going to be different from p, okay? Which means that the agent learns on two models, none of which is the correct one, okay? So it's going to use some sort of combination in order to describe reality. This is a typical trajectory that describe a typical trajectory of the model. What happens when, how much time do I still have? Very good. So this is a typical trajectory of the model. This is you can see you can compute using all the things that I showed you before, the consumption of the different agent. For instance, in this case, in this specific simulation, the agent that asymptotically rule the market, so consume everything, is the moving average agent. So with this specification, moving average turns out to be a very good strategy, the best strategy that leads to essentially dominance of the agent using it. This is just to show you the kind of dynamic you can see in this simulation. But what I want to discuss better is this plot. Okay, I think this is essentially the interesting part. So what you see in this plot is I fixed remember that the agent learns on two models, and I fixed the two models. So I say that the agents in the agent's minds there are only two possibilities. The coin is always unbalanced, and the probability of getting head is 0.3 or 0.8. These are the only two possibilities the agent contemplate. P is actually how much unbalanced the coin is, and we are going to move this probability between 0 and 1. Okay, so this is the reality. This is what the two models available to agent. Let's analyze what happens, starting with the black curve. The black curve is the Bayesian agent. Okay, so what happens to the Bayesian agent? Of course, when one of the two models, 0.3 or 0.8, when P is equal to one of the two models, this is not a misspecified situation. Okay, this is a well-specified situation. Now the reality is among the things that the agent can learn. Okay, and in this case, you see the average relative entropy goes to 0, the highest possible likelihood of the agent. So this agent is probably going to survive in any case. And this is the Bayesian. What happens if instead the probability is different? Then the agent, as you can see, cannot precisely replicate what's going on in the market. But let's compare this. What I want to stress now is comparing the different strategies. So the Bayesian agent is the black one. Let's introduce some degree of delay. Okay, so this is essentially the agent that learn a little bit slower than bias. And as you can see, this is going to increase the performance of this learning strategy in this area. Okay, and it's basically the performance are the same. You don't see the other colors here because they perfectly overlap above the Bayesian. And you can see also a very you can also see that in general, the limited memory Bayesian is a very bad strategy. Okay, in the large part of the support. Not here to say the truth. There are other interesting things that you learn. For instance, when lambda goes to word 1, which means that you consider a Bayesian agent that update very slowly its beliefs. In this case, as you can see, for all this region of parameter, the agent get a 0. Now, let me just show you, and I conclude, what happens if instead of considering a parametric, because this is happy, okay? The conclusion of this plot is averaging is good, okay? If I slow down in learning, look, I improve my performances. If I take a moving average of my prediction, again, I'm improving my performances. So it seems that the behavior goes in one direction, okay? The more smoothed I am, the more I average, the more I slow down and I delay, that's a unique, I'm more robust. This is already, is it true? Well, if you change the kind of misspecification, you partly destroy this vision. And this is a parametrically misspecified model. I'm almost finished. This is there is just another slide. Now, instead of having, the truth is no longer an IDD process, now is a Markov process. So the idea is now not only the model cannot be learned, but now the model belongs to a class of models which is different from the previous one. Okay, in this case, and this is the last slide, in this case, as you can see, there is a large area. Oh no, sorry. There is a large area in which only for instance, the stupid strategy of limited memory Bayesian learning that before performed very badly. Now there is a large area in which actually this is the best possible strategy among the old strategies that we have seen. So essentially, what's the message? Let me move to the conclusion. The message is, well, generally, when you consider misspecified situation, the predominance or Bayes rules or learning rules based on Bayes is challenged. Not so much in parametric when you have a problem of a parametric misspecification, but if the misspecification is huge, then very simple and apparent and seemingly stupid rules do actually behave very well. And that's it. Thank you very much. Sorry for the